Hello, I'm Joe Konstan from the University of Minnesota. I'm the chair of this session on understanding and modeling preferences. I think you'll be glad you're here, and more important, at the end of the session, you'll understand exactly why you're glad you're here and be able to model it in much better detail. We have 6 wonderful talks. One administrative note before we start. If you have questions as the papers are being presented, please navigate to the details of that paper and excuse me one second. So please navigate to the details of that paper and ask it under the Q&A in Whova. Finally, let's move on to our first speaker. Jinju, take it away.
Hi everyone. I will just share my screen. Thank you for coming to this talk. Today I'll be presenting our paper, TAVA, Two-Headed Attention Fuse Autoencoder for Context-Aware Recommendations. This is a joint work by University of Toronto and P7A with Joey, Felipe, and Max. The recommendation task we are considering here belongs to implicit feedback. In many cases, interactions such as purchase history or clicks are taken as positive signals, while explicit negatives are missing. It has many practical applications, and sometimes it's just the only type of data that's available to us. Collateral filtering is the standard approach for solving implicit feedback problems. Many approaches have been proposed to tackle these implicit feedback problems, including autoencoders. As the figure on the right shows, autoencoders encode interactions into a latent space through a fully connected layer, and then decode the embedding to generate predictions. While it is a strong baseline, it shows strong popularity bias as seen by others and also in our experiments. User review text, however, has attracted increasing attention as a rich source of set information that can be leveraged to improve recommendation accuracy. It is also very personalized, and we hypothesize it can be leveraged to combat this popularity bias. However, many existing work lacks an effective way to correlate meaningful information between user-item interactions and reviews. Many methods, such as autoencoders that only use user-item interactions, exhibit strong popularity bias. Both limitations hinder general performance of recommender system. Hence, our contribution addresses the 2 problems by introducing early and late fusion modules between user review and interactions to model deeper correlation between embeddings. We also leverage a closed-form noise-contrasted estimation (NC) objective to mitigate the popularity bias. Here's an overview of our architecture. As you can see, it consists of a preference encoder that's used to process user implicit feedback, a review encoder that's used to process user review information. Both of them produce a latent representation. The latent representations are then fused in our late fusion module. After that, we have 2 decoders that we use to decode predictions. Similar to the encoder part of an autoencoder, our preference encoder is a multi-layer perceptron that's used to encode user-item interactions. For the review encoder, a bidirectional LSTM layer is used to produce contextual embeddings for reviews. We apply attention mechanism on both word levels as well as on review levels to pick relevant information both within reviews and between reviews. One main novelty of our paper is we have an early fusion module in the review encoder that takes the preference encoder output, which represents preference for each user, and fuses with individual review of that user. By doing so, we provide an opportunity for individual review to interact or correlate with user preferences. And this allows user implicit feedback representation to guide review level attention weights. After obtaining the 2 representations, we need to combine them in late fusion module. Intuitively, this can be done with a simple concatenation. However, Because we have two different modalities, concatenation could be ineffective to capture this correlation between the two representations. We use cross-modal fusion to properly combine the two modalities. Specifically, we first map each representation to a common latent space. Attention is then applied to this common space to fuse the two representations. Fusing with softmax attention has a clear advantage over concatenation, so that the model can explicitly decide how much weight is given to each representation. Lastly, this is our two-headed decoder. We want to mitigate popularity bias while still maintaining good recommendation performance. To do so, we first transform user-item interactions to a depopularized version of it. The result of this transformation is the optimal solution for a noise-contrasted estimation objective. Intuitively, this objective scales down popular item interactions more than unpopular items. For the NC decoder on the left, it reconstructs this depopularized version of user-item interactions. This is critical to mitigate the popularity bias. For the preference decoder, it reconstructs the unmodified user implicit feedback. We use mean square error as our loss functions for the two heads, and the sum of the two losses are used to train the model end-to-end. During inference, we use the prediction results from the preference decoder. We evaluate our results on 6 recommendation datasets that have both user-item interactions and reviews. 2 of them are Yelp, which are related to restaurant recommendations. The other 4 are Amazon recommendation datasets, which have diverse domain setting and size. We order these datasets here with ascending order of sparsity. We use 5 standard metrics to evaluate the performance of baselines. Specifically, they are R precision, NDCG, precision recall, and mean average precision. We compare against 5 classical recommendation methods that utilize user-item interactions only. We also compare our results with term from gate to state-of-the-art recommendation methods that incorporate user review to make better recommendations. We show recommendation performance on Yelp 2013 at Amazon CDs and vinyls. The first one is the smallest one, and the last one is the largest and most sparse one. On both datasets, our method TAVA outperforms other baselines consistently. It can also be seen that the gap between TAVA is smaller for term and gate compared to other baselines that only use user-item interactions information, suggesting including review information is generally helpful to improve the performance of the model. We also study the level of personalization by our methods. We use the number of interactions item has as the popularity measurement. This is a personalization plot for Amazon video games. Here, x-axis represents item popularity. A larger value indicates more popular items. We see that Autorec CDAE exhibits strong popularity bias and achieve relatively poor performance. In contrast, other baselines such as Gate and VAECF mainly recommend less popular items with sharp peaks around very unpopular items. TAVA, however, instead of being extreme in either end of the popularity spectrum, diversify its recommendation in a more even way and is able to capture user preference for both popular and unpopular items. It can be seen that we successfully mitigate the popularity bias by other autoencoders such as Autorec and CDAE. Lastly, we visualize attention weights in our review level and word level attention mechanisms. We show both types of attention here. The reviews are taken from Amazon Digital Music and belong to the same user. The color represents attention weights, with darker color indicate larger attention weights. We see that review 1 and 3 is focused more compared to review 2 and 4, since review 1 and 3 are more specific, whereas the other 2 are more ambiguous. For word level attention mechanism, the model focuses on words such as great, favorite, or like that express direct preference. The model is also able to attend to some reasons why the reviewer likes a particular CD, such as singing and dancing. In conclusion, we introduce a method in the implicit feedback setting that mitigate popularity bias by leveraging user review and an NC objective. We introduce early and late fusion as a novel way to model deeper correlation between user review and user item interaction representations. Future work will be to extend TAVA by considering other data sources, such as item images, video, and audio. With that, I want to thank you for your attention.
Thank you so much, Jen. I see we have some questions coming in. As they come across, let me just start with something that, as I was looking, jumped out at me. It seems like the nature of your processing of reviews would work much better in domains where people write preference as the focus of a review, like they might on an item of music on Amazon, than a domain where their review is mostly descriptive, like you might find in movie reviews. You highlighted that seems to be where the model focuses. Did you also analyze whether adding reviews gives you more value in certain domains versus others?
Yes, certainly. So as you can see that for this attention mechanism, for this data set, which is the Amazon music data set, it mostly focuses on kind of this preference aspect. We hypothesize is mainly because we have this early fusion, also late fusion modules that guide this attention weights, right, with the preference representation, the preference latent representation. And yes, if the reviews are more descriptive, which does not really reflect a user preference, then in our case, using these review information will help less, because we are trying to predict whether a user will like an item or not, rather than kind of, we are trying to synthesize the summary of an item. So yes, definitely the reviews is more helpful if they are more related to user preference, if they are more specific rather than these sort of kind of, just, a really short and then, not very informative descriptions.
Okay. Another question that came in about the reviews was asking, how's performance affected in multi-language reviews where some sort of code switch or changing from one language to another happens in the middle of the review? Did you run into this, and do you have any comments on that?
For these Amazon data sets, I think they were kind of like pre-processed or cleaned when we get the data set. So they really don't have the specific issues, because these data sets, I think they are pretty standard, and then it doesn't really have kind of this multilingual issues. But for sure, if we have kind of train a model in one domain, let's say one specific language, and then we kind of need to do the sort of recommendation in another language domain, then certainly I will expect some sort of distribution shift, because the language itself, also maybe how people write or structure their reviews. So for sure, this will be kind of an interesting problem to look at. But for our data sets or for our problem setting, we didn't really run into this problem because of the kind of standard, the sort of data sets that we used.
Wonderful, thank you. Another person was asking a technical question. Why do you use an RMSE loss function to train a top-end recommender?
So for a standard autoencoder, people typically use this mean square error or MSE to do the sort of reconstruction. And then we also find out it gives a good performance. For the reason why for both of these heights, we use MSE, it is mainly because we find that doing so, the embedding it learns in this latent fusion, which will be kind of backprop from the two heights, it gives a more kind of coherent embedding. If you apply kind of two different loss functions, it seems that this kind of latent representation here will get slightly confused, which does not lead to a good performance. So it has both kind of this empirical reason as well as kind of some theoretical reason, because people typically use MSE to do reconstruction.
Okay, and we have time for one quick last question here. Is the attention mechanism still useful if the user data is not reviews and user click and impression?
You mean, is it more you mean when user does not have clicks, but other source of kind of preference is the review?
Exactly.
Yes. So in theory, because if you have some review information and then you use kind of this sort of attention to process this, then it should give more kind of information when you kind of use these representation. But if this is some sort of ratings, I think it will still help because the rating can be from 1 to 5. But if it's some other sort of kind of preference that's kind of like a little bit different, say, the time you spend on something, then I suspect it could be some sort of, engineering that you need to figure out in order to achieve this comparable performance. Yeah.
Well, thank you. And Liz, thank you again for your talk. And we will move on to our next speaker. Our next speaker is Scott Sanner. Scott, take it away.
Okay. Okay, can you see the slides? Okay, can you see the slides?
Yes, perfectly.
Okay, great. Okay, thank you. This talk is a ranking optimization approach to latent linear critiquing for conversational recommender systems. Sorry, it's a very long name, but I like to be very explicit in naming. I'll explain what this is about, but it's about critiquing and conversational recommendation. And I'm Scott Sanner. My co-authors are Hanze Li, Kai Luo, and Gagwu, and we're from U of T. Okay, let me start off with a news recommendation scenario from December 2020, just to get you in the sense of what we're doing. Okay, so I say to my trusty news assistant, what's trending right now? And the assistant says, here's some technology news. This is a little while ago, but Elon Musk unveils a brain chip implant. Says it's like a Fitbit in your skull. Now, some people may like that. Personally, me, brain implants worry me, right? So I asked my news assistant, is there anything less dystopian in the news? And my assistant says, sure, here's some encouraging international news, right? This news is about progress on the COVID-19 vaccine around the world. So that's certainly good news. So that's piqued my interest. What else is going on with COVID-19 these days? And so I ask again, is there any other interesting news? And the system says, well, my very intelligent assistant says, well, I'm not sure if it's interesting, which is an unusual perspective on COVID-19. And we have Trump claiming it's a badge of honor, right, that the U.S. is topping the world virus cases. I would certainly classify that as unusual. Okay, so what's the point here? We're doing language-based critiquing, right, in recommendation. So you repeat the following loop until the user is satisfied. You recommend an item, and the user says, great, I'll take it, or they give you a critique. In this case, the critique is language-based. Okay, and so there's a lot of great historical work on critiquing that was a bit more based on explicit aspects or features. Here, we're assuming language is the source of the feedback, and that's, of course, also the source of the problem that we have to solve. Okay, so we're looking at critiquing or historical critiquing methods meeting embedding-based recommendation. In modern language-based machine learning and deep learning, it's all based on latent embeddings of language. If I say I want something less dystopian, or I want something that's more interesting, right, I have to interpret what that means, and word embeddings can do that. The attributes of news, right, are not always also explicit. I mean, no one's necessarily going to label, Reuters is not going to label news articles with the label unusual, or at least they won't usually do that. And so we also have this fact that the traits of news, right, are also latent. Okay. And not only is the language aspect of this language-based critiquing latent, but also, standard modern recommendation systems are also use latent embeddings. Okay, so the key question we're trying to answer, and I've actually been trying to answer for the last year with my group, we have a number of papers on this topic, is how do you combine the user's latent preferences and the latent embeddings of their language-based critiques? You can average them, right? That's the simplest way, and we'll compare that later, but there are more sophisticated methods that we want to look at. Okay. So the key question is, right, how are we going to combine embeddings, latent embeddings with user preferences and critiques? And so this work most closely follows up on work we had just done at WW20 called Latent Linear Critiquing. And there we tried to propose a linear program to find a good weighting of the embeddings. And the one thing is, this was trying to maximize score difference. And what we found when we looked at this work more closely is it encouraged extreme weights. And so we thought in this work, let's take a software optimization approach. We just want to move the ratings in the right direction. We don't necessarily want to maximize that the scores between things that were critiqued and non-critiqued are maximally different, right? And so we're taking more of a ranking style approach here, where we basically just say, based on critiques, we want things to re-rank. And we just want to perturb the scores enough to re-rank them, but we don't want extreme rankings. And so that's the whole motivation for this work, is to take a ranking-based approach, essentially building on rank SBM ideas going way back, and encourage less extreme weights, and hopefully beat this work that we had done at WW20. Spoiler alert, we do. Let me show you how. Okay, so I'm going to skip the notation, just kind of define it implicitly. I would hope everyone is aware of basic matrix factorization methods for recommendation. So we have a user, item, rating matrix R, and we're going to factorize that into a user hidden embedding matrix, right, and an item hidden embedding matrix, right? Multiply these two, of course, and I'll recover the ratings. Now, we're not only working with user preferences here, we're also working with language. And so, sorry, you can use any matrix factorization method you want. Here we use one at HCHI 16. Okay, so we not only have user and item data, but we also have now user key phrase data, which we're getting from reviews. And we also want to map this into a latent embedding for the user, right? So we'd like to multiply this, the user's key phrase usage times some embedding matrix and get out another embedding of the user, but this time we got the embedding here from the user from the key phrase usage of the user as opposed to their item preferences. Now the thing is, whether we embed from a user's language usage or we embed from their preferences, right? We want these two embeddings to be equal. So once we've done that, and we know that the key phrase usage is given, and this is fixed because we already learned it up here, then we know that we can basically just learn this as a simple linear, linear regression or a matrix inverse. Okay. So now what we can do is we can take user preferences and embed those into user space, into their latent embedding space. We can take key phrase usage, language usage of the users, embed that into the same, co-embed that in the same latent space. And now we just have to manipulate these different embeddings. Once we have the embedding, we can always multiply it by the decoder and reproduce the predicted ratings. Okay, let me look at time here. Okay, I'm going slower than I thought. Okay, so let me speed through the rest of this. Okay, so the key idea is that if someone critiques, say in the beer review data set, if they critique bitter, right, it's pretty clear that your bitter beers should drop in rank. Now, we're relying on reviews to judge whether beer is bitter, so not everything is explicit, and we're relying on the embeddings of the language of the review and the key phrase to generalize, right, beyond explicit labelings. Okay, and so just for notational purposes, let I plus be the items with high frequency critique phrases. Okay. Intuitively, we want these items that were critiqued to fall in rank. I minus, right, were the things that didn't seem to be critiqued. And these are things that we probably don't want to affect. And in short, we're simply going to, we have iterations of our conversational critiquing. We have round T minus 1, we have round T. And what we want basically is for the I pluses, the things that were critiqued, right? We want their value or their rating to fall, right, in the next iteration. And likewise for things that weren't critiqued, we would actually like their rating probably to either stay the same or increase. But I'll just say increase here. Now you might wonder if we need both constraints. Hanze just got some results to me last night that said yes, we do better with both sets of constraints. So you just don't want to, you just don't want the I plus items to fall, but you actually do want the non-critiqued items to come up in rank a bit. Now everything's linear here because we can put a lambda weight on the user embedding. We can put a lambda weight on all the language embeddings. We just find the right weighting lambda and multiply, and then we get sort of one embedding for the user and all the critiques together. Combine that by the decoder, we can reproduce the ratings and we can recommend. Okay, so in the interest of time, I won't go over the full LP. It's basically just an LP version of the rank SVM. We have standard sort of rank SVM style constraints. I will point out here, just we found that by default, we want to penalize deviation from the uniform weighting. So if there's not enough data, then basically the system will kind of default to the uniform weighting, which also makes a good baseline, which we'll compare to. And we also try a different weighting where we always give the user's preferences 1/2 weighting and all the language preferences the rest of the weighting uniformly. We also compare it to the WW20 work. We simulate user critiquing. I'm going to skip the details here. It's in the paper. I'll just give you one key result. Comparing to the averaging methods, comparing to the previous WW paper, which is score-based re-ranking, we do see up to a 1 to 3 times improvement from this sort of softer manipulation of the critiques based on rank constraints as opposed to score max position constraints. And that's really, I mean, if you take one idea away from the paper, it's that we're trying to combine user embeddings and critique embeddings. And our previous work was a bit extreme in how it would weight things, and this work uses rank-based constraints to change ranks of items over the critiquing stages and gives you softer perturbations in the weightings and typically leads to better performance, as you'll see across the board. Okay, and just in the interest of, I don't have much time to go into more detail. So with that, thank you, and I'll take any questions in time remaining. And of course, feel free to email me after the talk as well.
Thank you, and we do know that people can reach you through Huva afterwards. I'm just going to start with a really, I think, naive question here, but I don't know, which is, how do we deal with a technique like this when a particular attribute is an asset for some products and a liability for others? And so, to use your example from the beginning, you don't want dystopian news, but you might like dystopian fiction, and you might be talking to the same assistant and, critiquing things like you might also like bitterness in your beer, but not like bitterness in your fruit. Right. Is there a way to think about how to get those interactions so that the scope of something being negative is limited to a particular product set?
Well, so the setting here, we are training, right? We have beer reviews and Yelp reviews, and so all the embeddings are specific to a product set to begin with, and then we are working with session-based preferences. So you say in the session, I mean, your long-term preferences may say you like things dystopian, but today you're not feeling very dystopian. And so your critique says, I don't want dystopian things. And that's a language-based critique. And we know that, okay, well, now all the dystopian things and data set that we know about, they should drop in rank. And so I think the language gives you very session-based manipulation. As soon as the session's over, all these lambdas and all the weightings disappear, and you start from scratch again. We always start at the first round with the base user preferences and nothing else. So hopefully the language you're giving is going to help specialize your preferences for this session.
Okay, that makes sense in the context. One last question, which is there value and could it be incorporated in this technique to include positive critiques and not just negative critiques? Yeah.
So yeah, for sure. I think that they're completely symmetric, and if we didn't handle it in the paper, it should be easy to handle in practice. If you say I want more of something, then that just reverses the rank constraints.
That seems straightforward enough. Well, thank you again for this paper, and I will remind people who want to interact with you that they can message you in Huva or leave something in the detail page for this paper, and we can follow up with you afterwards.
Okay.
Our next speaker is Yin Zhang. And Yin, take it away.
Yeah. Thanks. So, hi everyone, I'm Zhang from Texas A&M University. Today I'm happy to introduce our work, Content Collaborative Disentanglement Representation Learning for Enhanced Recommendation. So for recommendation to predict the user preference towards items, for example, the user preference towards the address, there are typically two ways. One is to find similar users or similar items, and then based on the similar user purchase history to predict the user preference towards the address. Another is to build the user and item profiles. For example, using the user age, job, and items image descriptions information, and to build the profiles and using the profiles to predict the user preference towards items. Modern recommendations usually combine the collaborative signals and content signals to predict the user preference. However, the learned features from the two types of information could be highly entangled. For example, the user prefers the dress because of the dress appearance and high quality. There are many similar users who prefer the dress because of similar reasons. And at the same time, we want to utilize the dress image information to help the recommendation. In this situation, if we consider the collaborate signals and content signals and directly concatenate them to predict the user preference, the learned features from the two types of information could redundantly encode the visual characters of the dress, leading to the feature duplication and high feature correlation problem. Thus, when content and collaborative information are both considered to learn the user preference, it could lead to the feature duplication and high feature correlation problem, limit the user and item representation capability, and overweight those correlated features. It can further lead to the suboptimal performance and unrobust recommendation. Thus, in this work, we aim to learn the disentangled representations based on the both user behavior data and content information. First, a little bit introduction about disentangled representation learning. It aims to identify features that are relatively not influenced by the other feature changes. For example, I have several images here, and we want to learn the object shape, color, and position features that are relatively not influence the other feature changes. Like the change of the object shape does not influence the object color. The disentangled representation has shown robust performance and high interpretability in many areas, especially in computer vision. And one commonly used strategy to learn the disentangled features is based on the statistical independent. Okay, back to our problem. How to learn the disentangled features from both content and collaborative information for recommendation. There are two key unique challenges. First, different from many problem settings that features are explicitly known, such as the colors and shapes in the image. Here, the user-item interactions does not necessarily map to explicit features. So, such high heterogeneity between the implicit features in user-item interactions and explicit features in content information makes it extremely hard to learn the disentangled features between the two types of information. And second, the disentanglement between the content and collaborative information only ensures the features that are learned from the two types of information are different from each other. However, the features learned within each type of information could still be highly entangled. So how can we deal with such disentanglement within each type of information at a graduate level is also challenging. So consider those two challenges. We proposed a two-level disentanglement approach called DICER to learn the disentangled features when considering both the content and collaborative information. And concretely, it contains 3 steps. So in the first step, we design content and collaborative disentanglement based on the independent marginal distribution to ensure the learned features from the two types of information are different from each other. Then in the second step, we have a feature disentanglement at a gradual level that decomposes features for each type of the information. With theoretical shows our learned features can disentangle at a gradual level. And last, we have co-decoders to ensure the high quality of our learned features. And notice here in our proposed model dicer, there are two important variables. One is ZIC, which represents the content features from item I, and another is ZIO, which represents the content disentangled collaborative features. That is learned based on both user-item interactions and item content information. I here means the item I. And let's first take a look at the content collaborative disentanglement step. We designed the user feedback XI to be generated from all features that influence the user preference towards items. And then we decompose the AI to be the content features derived from item content information, the IC, and the content disentangled collaborative features, the IO. Thus, the distribution of the I can be represented by the joint distribution of the IC and the IO. Then we utilize the disentanglement properties that the IC and the IO is statistically independent. Thus, the joint distribution of the IC and the IO can be represented by their marginal distribution. And based on this equation, we can get the evidence lower bound of the XI, user feedback XI. This is for the content collaborative disentanglement. And in the second step, we further decompose the KL term in the evidence in the previous evidence lower bound. And as shown here, it has 3 components. And based on the 3 component representations, we further refine our loss function to encourage the feature disentanglement within each type of information at the gradual level. And details, please look at the paper. And also the third step, please look at the paper. So here is our experiment results of our proposed model dicer compared with the other state-of-the-art method across 3 datasets in Amazon dataset. And the last column shows the improvement of dicer compared with the next best performed baseline. And since all the numbers are positive, it shows that dicer consistently outperforms state-of-the-art method in recall at K and NDCG at K. And recall that for our important variable content features, DIs, and another is content disentangled collaborative features, AIO. We further visualize the 2 learned features. And here it shows the results. The first one shows our learned content features. We can see it separates items based on item-oriented content informations, such as the categories without category information. And the second figure shows our known content disentangled collaborative features. We can see that it clustered items by the user-oriented information. For example, it clustered users by the female and male information. Thus, by disentanglement, our model can capture very different informations in the representation. Thus, it can increase the item representation capability to capture more diverse information that influence the user preference towards items. And in sum, in this work, we studied the relations between the content features and collaborative features. And then we proposed a 2-level disentanglement approach that suppose both content collaborate disentanglement and feature disentanglement. An experiment shows that the learned representations can capture very different information and brings large improvement for the recommendation. And in the future work, we are very interested into extending DICER to other scenarios, such as consider the item social network information. And that's all. Any questions?
Well, thank you. We actually have a whole bunch of questions that people have submitted. And so let me just jump quickly to them, starting with a question about whether your technique could be used to create more explainable descriptions for recommendations that might help with trust. So could you come back and say, something about because you like this aspect in either content space or because of something in user space? Have you thought about how it could be used in explanation?
Yeah, that's a very good question. Yeah, so for the disentanglement here, our work mainly want to disentangle the features to make the recommendation robust. But one of the very benefit for disentanglement learning is that they have a high interpretability, that they can disentangle the features to have a better understanding about what features we learn. And here, through the visualization, as shown here, we can find we have two important features. One is the IC and one is the IO, and they contain some interpretabilities. For example, the ZIC contains the content information, and the ZIO contains the user-oriented information. And also in our paper, we studied each dimension, which captures each dimension captures. And we find that our learned features actually capture some meaningful features. And details, you can look at the paper here. I did not have the figures.
Okay, thank you. Another question was asking, he said, the improvement you show over the state of the art is awfully impressive. Is this something you've been able to reproduce in other data sets?
Yeah, that's a very good question. So we haven't tried the other data set, but our observations is that when the data set is sparse, it has a large improvement. But we can try a different data set, more dense data set, to say whether it has whether it has an improvement. But that's a future work. We can definitely try.
Okay, and somebody did ask a specific question about this table where you have what it looks like it's the hit ratio, hit rate at 5 and at 10, and the values are larger than 1. I was wondering, is this a hit count? The HR at 5, HR at 10? We're sort of expecting those to be ratios.
Yeah, that's I should make it more. Those times, because our data set is very sparse, we consider all the items actually. So here it shows the actual number times 100%. So you can look at the measurement. It's the percentage. Yeah.
Okay, so 2.6 is 2.6%.
Yeah, exactly.
Okay, that would explain that. And I think we have time for one more quick question. I think the one we'll ask here is about whether this approach could be used for other kinds of disentanglement. Could you disentangle different categories of content-based features, for instance, rather than just content from collaborative?
Yes, it can definitely used for different content of information. We have two levels of disentanglement. One is disentanglement different types of information, collaborative and content. Another level is the feature disentanglement. That is when, for example, when the content information we disentangle the features learned in the content information. So it can be applied for different content information.
Wonderful. Well, thank you again. Really appreciate it. And with that, we're going to move to our fourth speaker, Tobias Schnabel. Tobias, take it away.
Yep. Thank you. Let me share my screen. I hope you can see that and hear me fine. 1 second. All right.
We see it.
Thanks. Thanks, everyone. My name is Tobias Schnabel, and this is joint work with Gonzalo, Ramos, and Saleema Amershi, and I'm going to talk about our paper, Who Doesn't Like Dinosaurs? Finding and Eliciting Richer Preferences for Recommendation. So, the main goal of recommender systems is to connect people to the items they want. So I think we can pretty much agree on that. And recommender systems essentially act as intermediaries. So they infer people's preferences and then retrieve items based on those. And for this to work, it is really crucial that the system understands the preferences correctly and can, if not, can be corrected. And so in this paper, we focus on the design space of preference elicitation methods that really help the recommender system infer the preferences better. A very important trade-off to consider when designing preference elicitation methods is the one between how rich is the information we get and versus how demanding it is on users. For example, binary feedback, such as thumbs up, thumbs down, or liking, is fast but limited in the information it conveys. In contrast, conversational systems offer rich information, but they pose a high effort to users. And in this work, we explore this design space guided by two questions. First, what are the patterns in how people express their preferences? And then second, can these systems help to improve recommender systems? And to do this, we essentially carried out a need finding study where our goals were to understand how people articulate their preferences, and where we really wanted to give people as much freedom as possible so that they can, so we offered them the full richness of interaction. They can draw, annotate, and talk and gesture. And then we use that where we wanted to distill a general set of patterns to organize preferences around decision making. And the setup was as follows. We had an in-lab study with 23 participants, almost balanced in terms of gender. Then we had a curation task on 2 domains. We had people work with sets of 12 images and then a set of 12 articles each. And the task was that each participant had to choose the top 3 items. So the items they liked the most, and then explain their choice. And we framed it as kind of a curation task similar to what or bookmarking task similar to what they would go through on any of the online platforms or apps like Pinterest. So here is what it looked like for the article curation task. Here is kind of a snapshot on the left showing that the participant organized it roughly in kind of mini stacks and labeled it neatly. Not everyone did that, but that's just one snapshot. And then on the right is a snapshot of a participant's desk after or during the image curation task, where they also roughly kind of organized the images in piles according to categories and then chose from those. So what were the outcomes of the study? Well, as the authors, we sat together and went through kind of an iterative coding exercise to develop the following patterns. So we split it into 2 independent concepts, and each kind of preference statement can be annotated then with along these 2 dimensions. So the first dimension is relevance, like how a person relates to an item. And there we had 4 values or possible codes. An item could be relevant because of actions, biases, routines, or because of certain attributes it had. It could be relevant because of people the person knew, or emotions, imagination, or curiosity that they felt. The second concept was the temporal concept. So when did this relationship start or end? So did it start, end in the past? Did it start in the past and is still ongoing? Or was it in the moment or not started yet? To make this more concrete, here's 2 examples. One participant said, I love waterfalls. So that would be a preference statement connecting it to kind of biases or general kind of interests, so R1. And then it would be, it started in the past and is still ongoing. So that love for waterfalls, so T2. And then how did they make this? Were these pieces glued together? That would be an emotion or like a curiosity, so R4. And it was in the moment, so that was T3. All right, so what else did we find in the studies, or what are the takeaways here? Well, first of all, we saw that in terms of decision-making strategies, many participants showed a 2-stage approach, which is also known as consideration set formation in marketing. And so one implication is that we need to think about, or we could think about supporting decision-making better. For example, via short lists where people have like a temporary list where they can add items that they're interested in. And I had some previous work that showed that this is actually helping people make better decisions and improving also recommendation performance. Then in terms of differences between the domains, we had a higher prevalence of emotions and in the moment kind of reactions for images. So that makes sense, I would say. As well as I think it implies that we may need to rely more on user-generated tags and descriptions to capture those aspects where current content understanding falls short. And then in terms of, we also just saw that there was this lack of expressiveness. So certain dimensions were not supported or are not supported by current preference elicitations instruments. So we need to add more granularity and support for those. Now, moving on to the second question of how we can use these patterns to improve recommender systems, we did a case study where we used those patterns to improve the design of an onboarding questionnaire. Our goal was to have less or comparable effort for users, but yield more accurate recommendations. So based on these patterns, we designed an onboarding questionnaire we called Tell Why. And so we had 4 questions that correspond to various factors and concepts that we uncovered in the earlier study. And we focus on factors that could generalize. So asking for certain people they know probably is not likely to generalize. So we left that out as an example. More details can be found in the paper. So on the right is what it looked like. It was just a simple kind of option checkbox design where people could check the things they were interested in or choose none of the above. And then we compared this onboarding questionnaire to other common methods, like a category-based one where you just select topics you're interested in, a personality-based one. We used the TIPI questionnaire that had 10 questions about people's personality. And then an item-based one where they just rated a bunch of items, which is, I think, a very commonly studied one. And we measured how the user effort on the NASA TLX score, as well as recommendation performance, where we used the onboarding questionnaire as an input and then had the chosen items in the various sessions, so images and articles as the recommendation target. So we repeated essentially a similar design that people went through also in the need finding study. So the results here are from 518 MTurk participants. we saw that the personality-based onboarding method fared worse, and TAVA had the highest accuracy. Also note that this is a hard task, as popularity shows, like it has relatively low performance. And user effort, we found that TAVA had comparable or lower user effort. So really, to wrap everything up, what are the patterns in how people express their preferences? Well, we proposed a coding scheme for a preferences relevance type and the temporal dimension. And then can these patterns help to improve recommender systems? We had this case study showing that you can design a better onboarding scheme by essentially adding more support for the various concepts. And TAVA showed a higher accuracy under lower or comparable effort. So if you kind of plot it in the space of effort and accuracy, TAVA is on the Pareto front. And then future work could look at, using those codes to also explain decisions better from the recommender systems or for critiquing. And so you could use also then these codes, as I said, to refine things online in addition to just onboarding. Okay, thank you.
Well, thank you. You've inspired a bunch of questions, but also some comments. I think according to the consensus of our attendees, everyone likes dinosaurs. And so they like your title. They also like dinosaurs. I tried to find people who didn't like dinosaurs. The most I could find were sort of small turtles that had been eaten. So we're all on the right track. But let's get to the substance here, which is, I'll start with the first question that I saw, which is, did you also consider the order in which people choose the preferences? Can your work help in designing sort of better runtime policies in contextual bandits?
The order in which people choose specified preferences. So what we did in this study was to ask people when they made a decision, like what were the reasons for you choosing something? And so in that sense, we didn't have a progressive kind of state of preferences, but I think it is a very interesting question of how do you, we have now this rough taxonomy of how you can map preference or what you can map preferences to, but it still doesn't tell you exactly like how to elicit those. And I think that it would be interesting future work. Like, how do you go from like a high level to like a more fine-grained understanding of, let's say, the like one of the categories, like the R1, like background interests or so, right?
Mm-hmm. Sure. I mean, that actually relates to another question somebody had asked about, could this taxonomy have turned out differently with, a different task, with a larger item space or a different specific domain like video or music?
I would say yes and no. I think what my intuition is that we try to make the taxonomy high level enough so that if you move to another domain, you would add probably maybe a few subcategories, or maybe you wanted to add a finer level distinction, depending on how, for example, we saw differences between images and articles. So in articles, people talk much more about the content of an article, and you might want to add more support then for these fine-grained. Or when you talk about products, people are talking more about the attributes, the item attributes there. So my intuition is that a lot of the higher level categories still carry over, but you would have to tweak maybe or add support for the lower level details.
Sure. At a broad level, is this something where you would see designing recommender systems that have as one of their parameters where is the user in their decision-making process, and adjusting the algorithm to respond to that alongside everything else that it's learning?
Yeah, I think that would be super exciting. And I think Amazon is already doing a little bit of that implicitly by adding kind of this comparison between similar products into their product page. But that is supposed to support people in this first stage of consideration set formation when they essentially want to narrow down the space of alternative options and then choose among those. But I think you can go further, and you can help people more actively kind of forming those sets and then arriving at kind of good decisions.
Wonderful. And one last quick one here. Someone's asking, I think looking towards applications, could this be used to design better onboarding of preferences for apps, music and video apps that are out there today?
Yeah, I hope so. I hope so. Again, you would want to understand a little bit better what specific kind of values you want to ask for. Like we populated the in our case study, we populated with our questionnaire with a bunch of like specific values, but those are domain dependent. So, but I think it is, if I want to get one thing across, I think it is really important to start with an understanding of where users are and what they kind of want, and then kind of support them in their task rather than kind of starting bottom up or so.
Well, I think it's always wonderful that we've got people in the audience who are thinking about what can I do with this next, which is one of the great things about RecSys. Thank you so much. And we're going to transition to our next speaker, Walid Krishan. And Walid, take it away.
Hi, thanks. Okay, I think you need to stop sharing your screen so that I can share mine. Okay, perfect. There we go.
We're good.
All right. Hi, I'm Walid, and sorry, let me just remove this. Okay, there we go. Cool. So I'll present our paper, Neural Collaborative Filtering versus Matrix Factorization Revisited. This is joint work with Stefan Rendle, Li Zhang, and John Anderson. And
hello, everyone.
papers in this session. Okay, a general approach for training item recommendation models is to learn an embedding representation for users and items, and then combine these embeddings using a similarity function. And one of the simplest choices for similarity functions is the dot product. So for example, when the embeddings are free variables, this would correspond to matrix factorization. The embeddings could also be functions of user and item features, as illustrated in this figure. For example, the user embedding might be a neural network encoding a representation of the user based on user features, and same thing for the item. Recent work has advocated for replacing this dot product by a learned similarity function. The simplest example is to concatenate the embeddings P and Q, and then feed them into a multi-layer perceptron, or MLP. And this approach is usually referred to as neural collaborative filtering in reference to this paper from 2017. So we'll call it NCF for short. Two arguments have been used in support of this approach. One is the experimental results from the NCF paper, and two is the universal approximation property or theorem, which states that a large enough MLP can locally approximate any continuous function. And in particular, it should subsume the dot product. As a consequence, MLP learned similarity has become the de facto standard in many academic studies, and it's considered as a strong baseline. In our paper, we revisit both of these arguments and show that they are flawed. So let's start by revisiting the NCF experiments. Our setup follows that of the NCF paper. We run experiments using the same published code and the same training procedure on two datasets, MovieLens 1 million and Pinterest. The protocol is to hold out one item per user and then measure sampled recall and DCG at 10 with a sample size of 100. The models we compare are the baseline, which is matrix factorization, and then the NCF variants from the paper, from the NCF paper. And I should mention that in all of these models, the embeddings P and Q are free model variables. So really the only difference is the choice of similarity function. So whatever differences we can observe can be attributed to the choice of similarity function. Okay, in the following figures, the x-axis represents the embedding dimension, and the y-axis is the metric. Left is hit ratio and or recall, and right is NDCG. And the top row corresponds to movie lens, and the bottom row is Pinterest. Okay, so here we compare the dot product baseline in blue to the MLP learned similarity in orange. So we can see from this first experiment that dot product gives a much better performance than MLP. Now, a second variant proposed in the NCF paper is to combine MLP with a weighted dot product, where 2/3 of the embedding vector are used in the MLP and the other third is used in the dot product, which is given by this expression. So the only difference with the plain dot product is this vector of weights W, which are also learned. So we observe that this does improve upon MLP, but it's still worse than the simple baseline. The final variant uses the same model, so MLP plus GMF, but it trains the two components separately and then fine-tunes the combined model. And this again improves the performance compared to MLP, but it's still worse than the dot product baseline. In every instance except one, where the performance is pretty much the same. So it's important to mention that dot product was used as a baseline in the original NCF paper, and it was found to have a poor performance. However, that we show that carefully tuning the baseline actually outperforms all of the NCF variants. And this could be attributed to the difficulty of setting up baselines and tuning them correctly, as argued in a few references, including these two. So the revised results show no empirical evidence in favor of NCF. Let's now look at the second argument. So as I mentioned, it's argued that a large enough MLP is able to locally approximate any continuous function, so it should subsume dot product models. So here we run synthetic experiments to investigate empirically how difficult it is to learn dot product using an MLP. Specifically, we look at two things, how large the MLP needs to be and how many training examples are needed. So the setup is as follows. The embeddings are normally distributed, and the labels are given by the dot product plus a noise term, which is also a normal distribution. And we choose the variance of those two distributions in such a way that they align with empirical measurements from the Netflix prize. So we do this so that we have a guideline on what should be considered a significant approximation error. In particular, it took more than a year for the community to improve the RMSE by 0.01. So we consider this sort of a benchmark to be a quite significant difference. In fact, even much smaller increments have been published in the past. So in these figures, this value 0.01 corresponds to this gray line. So any approximation error above the line is considered too high. The x-axis is the number of users in the synthetic set. And the solid and dotted lines correspond to basically cold start versus warm start users. And finally, the different colors represent different embedding dimensions, with blue being the smallest and red the largest. So we also tried several sizes of the MLP. When we used the size that was recommended in the NCF paper, the errors remained too high. But even after increasing the size of the MLP, the error of course decreases, but the number of users that's required to reach a given approximation error grows roughly quadratically in the embedding dimension. So except for the smallest dimension blue, which is in blue, the approximation error stays larger than what's considered a very significant error. So beyond these experimental results, there's also a practical advantage of dot product that I'd like to mention, which is that in retrieval, so retrieval can be done efficiently for dot product using approximate inner product search. And these techniques are a priori not applicable to MLPs. And even if we were to do exact scoring for retrieval, the cost of scoring under dot product would be linear in the embedding dimension versus quadratic for MLP. So in light of these empirical results and also these practical advantages, we in general prefer using dot product over learned similarity. We emphasize that this is not a statement about whether neural networks are useful for recommendation. Rather, this is a statement about the choice of the similarity function used to combine the embeddings. In fact, many neural networks use dot products. For example, in a softmax model, if P is the input to the softmax layer and Q is the weight matrix, then the ith logit is simply the dot product between P and the ith row Qi. Okay, so to conclude, this work compared similarity functions for recommendation and showed that a carefully tuned dot product outperforms learned similarity models. It also shows that learning a dot product with the MLP would require a model that's too large. So we think that NCF similarity should be used with care in general, and dot product is likely a better default choice in most cases. Thanks for listening, and I'll take any questions.
Well, thank you for this talk, and indeed we have a bunch of questions pouring in, so let me just jump right in. Does the ability of the MLP to subsume the dot product improve if you provide the MLP with engineered features like P, Q, P minus Q, P times Q concatenated together?
That's quite possible, especially if we provide P times Q, then it would be trivial to learn a dot product, right? But that's not what is typically used when people say that they use NCF learned similarity. Usually they just use concatenation, or as I mentioned, there are some variants which combine this with a learned weighted dot product. But in that case, you're effectively decreasing the embedding dimension because you have to split the embeddings into things that use a dot product and things that go into the MLP.
Got a couple of technical questions. One, how the parameters were tuned in your experiments on the test set or a validation set. The other was, did you evaluate with non-sampled metrics?
Good questions. So we tune on the validation set, and then the plots that we show are on a test set that's never used for tuning. And as for the metrics versus sampled versus exact, I believe we measured only on the sampled metrics just to be able to compare with the published results of the NCF paper and other papers, which use 100 samples. So I don't want to give you inaccurate information. It's possible we have exact results, but I don't remember off the top of my head.
Okay, fair enough. Could you give any explanation why simple dot product outperforms multi-layered networks?
Well, one possible explanation is, as we showed, it is hard to learn a dot product using an MLP. So while it's theoretically true that a large enough MLP would be able to learn a dot product, so it would subsume dot product models, we show that in practice it would have to be very large to accurately learn the dot product. So it's quite possible that, at least on these data sets, on this experiment, a dot product is closer to the actual, to the ground truth.
Fair enough. Questions are pouring in. We're going to have to direct some of them that you can take a look at afterwards, but let me find at least one more that might be different from some of the others. What if you used matrix factorization to initialize vectors, but then transfer learn by neural networks? Would it be possible to beat MF alone?
So that is actually one of the variants that is used in the NCF paper, which is this pre-trained NCF plus GMF. So in that sense, we still find that dot product outperforms it, again, on these data sets.
Let's see if we've got one more we can throw in here that would be quick. Well, I think this is a good general one. Can you just elaborate on how the embeddings you used, that you fed into the dot product, are tuned better than those in the original NCF paper?
So we think that it's just a matter of hyperparameter tuning, basically. So one small change that we made that might have an impact in practice is we use explicit biases. So this does not change the expressivity of the matrix factorization model, but it's known actually from the literature that adding biases does improve empirical performance. So that's one one change. The other is, I would say, simple hyperparameter tuning. But again, it's hard to find the right hyperparameters. For example, we found that the models that were in the NCF paper were under-regularized in general. This is why, for example, the GMF, the learned dot product, performed actually quite poorly compared to regular dot product.
Makes sense. Thank you again. Wonderful paper, wonderful presentation.
Thank you.
We're going to move on to the anchor presentation of this session. Our next and final speaker is Mumita Bhattacharya. And Mumita, take it away.
Sharing my screen. Are you able to see my screen?
We are.
All right. Hey, everyone. I'm Mumita Bhattacharya, a senior applied scientist in ETSI. And today I'm going to talk about work that we did in ETSI jointly with a colleague of mine, Amay, query as context for item-to-item recommendations. All right. Oh, you're able to see the notes? Okay. 1 sec. Probably have to do a presenter mode again. Okay. All right. So in general, recommender systems is one of the main applications in e-commerce platforms such as Etsy, a two-sided marketplace. And one application of recommender system is to recommend items for a given product. So item-to-item recommendation. So here's an example. I'm showing a target item, and we want to show other items that we think the user might like, given the user is in this product page. And traditionally, such item-to-item recommendation systems are typically built using properties and characteristics of the product itself. And in this work, we show how we added additional context beyond just the properties of this item to generate these item-to-item recommendations. All right. So as I was mentioning, traditionally we use properties of the items, and typically, at least in the context of Etsy, we have been using content-based recommendation to generate these item-to-item recommendations. So basically, given the target item that the user is currently seeing, we generate features related to the properties and characteristics and historical interactions of the item and all the other items in the repository, in the inventory, and then train a machine learning model where the labels are implicit feedback from the historical interactions, and these model generates some kind of probability scores based on whatever we are trying to optimize that can then be sorted to generate the final ranked list of recommendations. However, in reality, in the context of Etsy, and I'm sure in many other platforms, the problem space to train such a ranker is pretty large. Specifically in the context of Etsy, we have more than 65 million daily active listings. So in order for us to train a model and generate a rank list of recommendation for each product, we will have to basically generate score for 65 million by 65 million, which is a computationally infeasible problem. So what we do to mitigate this problem is we generate our recommendations in 2 stages, which is, I'm sure many of you already are aware of. We start with, from the millions of listings in our inventory, we first identify, we retrieve few hundred products, which basically is often referred to as first pass or candidate set selection. And this is often done to ensure high recall. And then given these hundreds of listings, we can then use rankers, such as described in the previous slide, to generate the final rank list of items, and that is often referred to as second pass ranking. So in this context, I'll show how we generate a new kind of set where we add context of user intent and seasonality in the form of queries to generate a new kind of set, and then use different nonlinear rankers to rank those kind of set to generate final recommendations. So more specifically, the question we tried to answer in this work was, can we include context beyond just the attributes associated with the target and the candidate items? As an example, let's say the user is on this product page, red hat, and let's say it's Halloween time. The question we try to answer very simplistically is, should we show the user just other red hats, or should we show the user, given that this red hat has been purchased or interacted by other users in the context of Halloween, other red hats that are also preferable for Halloween times? How do we go about doing it? In order to do it, we end up developing two different approaches, which I'll describe in a couple of slides. So the first approach is an embedding-based nearest neighbor approach, where we extract top-end queries associated with each listing from the historical log data, and then train a simple skipgram model using listing and query, where this skipgram model during inference time gives us embeddings for a given query and embeddings for a given listings, and then generate for each given listing in the embedding space nearest neighbors, k nearest listings. So essentially, because they're generated from the same model, we are able to do nearest neighbor between the listings and queries. And eventually, for the k nearest neighbor, we use a FIAS API. And then, given this query and the top end listing given a list, top end queries given a listing, we basically are able to generate for each listing and its top end queries a list of candidates. That is a list of listings. So essentially, instead of going from listing to listing directly, we using this approach of embeddings and nearest neighbor, we are able to go from listing to query and then to listing to generate the candidates for a given listing. And I'm using the term listing, item, and product interchangeably. They're all the same. However, we found empirically during our experiments, based on the evaluation metrics that we use, which I'll show in a couple of slides, that a simpler approach actually outperformed this method as well as our current production system. And that approach was, we used search session historical data to generate candidates instance. So essentially, this is an example of a search session. So a user comes in, provides a query, let's say hanging shelf, and our search algorithms generates a list of items, and then a user interacts with a few of those items. We consider each item within a search session, let's say as a target listing, and then look for neighboring listings or items within that session that were interacted by the user, and start collecting them as candidates. And then we aggregate that across all the sessions where that particular target item was shown. This eventually gives us a list of candidates that has similar context, that is the query under which the target item was shown, while also capturing historical interactions that the user, across all users have interacted with given the search session. And then we basically do that across multiple days, and we experiment with, as a hyperparameter of this method, we experiment with the number of days we look at. So we start with 14 days, 1 month, and interestingly, during COVID time, we wanted to avoid the impact of COVID-related search only, which was heavily on mask and COVID-related items. So we increased the time window to 60 days and then 90 days, and that generated candidates. So once we have these two sets of candidate set, we would have to use a second pass ranker to rank these lists of candidates. For second pass ranker, we experimented with tree-based gradient boosted ranking. Specifically, we used the LightGBM API. And we ranked the ranker was trained on aggregate implicit feedback from different recommendation modules. and essentially treating this problem as a binary classification task where click and purchase was treated as positive and impression and view was treated as negative instances. Similar to probably many other real-world application, our training data was plagued with class imbalance. And we tackled this by using two approaches. One was random downsampling of the negative class, and another was instance weighing. And both these approaches, both instant weighing and random downsampling, reduces the training time and improve performance. So the one that we used for this experiment, the gradient boosted decision tree, was a point-wise ranking, but in the future, we also tried pairwise ranking, which further improved the ranker performance. So how did we evaluate the kind of set that we generated and compare the two different kind of sets with the kind of set that we had in production? We developed and used a few different evaluation metrics. The first one is the more common one, hit rate or recall, where given a target listing we gather all the co-clicked listing aggregated over visit as ground truth, and then calculate the hit rate, which is given by the formula here. We also used some custom metric for our problem. For every given listing in the context of Etsy, we have an associated taxonomy path. So for example, a table lamp, something like this would look like the taxonomy path. That is home and living, then lighting, and then table lamp. We calculate a taxonomy distance for each candidate listing compared to the taxonomy listing, target listing. So essentially, given to item A and B, we calculated the union over intersection of the taxonomy. So this gives us a taxonomy distance between two items. And we did that average calculation for all the candidates given a target listing. We also used some additional evaluation metrics, such as mean log price and standard deviation of log price. So this was primarily given the task at hand, which is to generate recommendations, additional recommendation that we think the user would like, given the product page the user is at. We hypothesize that we want to minimize the values between the target listing and the candidate listing. So essentially, negative, lower the difference between the target listing mean log prices and the candidate listing, the better it is. Similarly, average taxonomy distance and average unique shops. So we want the candidates to be as close to the target listing as possible. And our results—
Just a quick warning for you on time. Okay. We need you to wrap up in the next 2 minutes.
Yeah, I think I'll be good. And then finally, we also looked at some summary statistics like average number of recommendations per target and traffic coverage. Quick comparison of the current production system and the winning variant of our approach. We see that there was significant improvement. So with respect to hit rate and recall, there was around 12% increase in the hit rate. With respect to taxonomy distance, log price, we see a decrease. And as I was mentioning, lower is better because we want the candidates to converge as close to possible to the target so that we don't show the user drastically different things than what they are, the product page they are at. Similarly, unique number of shocks and taxonomy values are also shown here. Using this approach, we actually launched a few A/B tests. Wherever on the platform we had an item-to-item recommendation module, we launched them on listing page with paid traffic and signed in, signed out, and post-purchase page. And we saw significant improvement with respect to conversion rate and user engagement metrics, such as percentage add to cart and checkout. And I was unable to provide the numbers here, but we made significant GMV value as well from this switch of kindness set and ranker. All right, so to conclude, we show that adding additional contextual information that captures seasonality and user intent in the form of queries yielded an improved kindness set for item-to-item recommendation. And we also developed a few evaluation metrics as a part of this work to assess the efficacy of these new kindness set. And we hypothesize that these metrics can be used beyond the current use case. given the initial positive signals from this work, we are now continuing to add query context as feature in our second pass ranker as well, and add additional contextual information such as personalized information to our item-to-item recommendation. And you might have noticed that I skipped out a lot around what the embedding model was. I just said we generate embeddings. For this iteration, we use the simple skipgram model, but we are now experimenting with different embedding models, including the more modern attention-based models to generate better embeddings for the first approach. Thank you. You are muted, Professor Costa. I think you're muted. I can't hear you.
Thank you. I'm sorry. Thank you so much. We only have time for one question. I hope people will go, and if you will go and answer them afterwards, people would love to hear what you have to say. But let me ask the one that we'll ask here, which is, does your system take into consideration what many of us would call business rules, business logic, prices, margin, diversity of suppliers and other things in addition to the sort of pure recommendation?
Yes, that's a great question. So with respect to, I'll answer this in two phases. One is with respect to the modeling context, some of the terms that were mentioned, prices or shops or taxonomies, are included as features in our second pass ranker. But after the final ranked list of recommendations is generated, we also have a separate team that would add a third layer of filtering or any additional business rule required before they launch the experiment. In this context, we were able to launch the final ranked list generated by our model as is during the A/B test and also as a part of the product. But oftentimes there are initiatives where we might want to bump up some promo, like we were trying last year, trying to promote free shipping on $35 or above purchase. So some kind of business logic, if there is requirement for product, we often do that.
Wonderful. Well, thank you so much. And I know that our audience here wants to thank all six of you for what was really an engaging and educational session. Thank you all. And for the rest of you, there's continued activities, through the rest of this day, whatever time it is this day, wherever you are around the country in RecSys, around the world in RecSys. So have a great session, and thanks again to all of our speakers. Good day.